Today we're going to talk about linear approximations and differentials. All right, and I'll do more of a breakdown in class about kind of some of the stuff from the textbook, but the textbook does have a good introduction about linear approximations. Mine's going to be pretty brief, so I want to make sure that you, again, are reading Calculus for Dummies and also reading the intro part, especially of this lesson on 4.2, linear approximations and differentials. Okay, now, essentially I want to start by just looking at this first approximation here, all right? And I know it looks a little bit confusing. There's a lot of stuff going on, but essentially this is just a manipulation of point-slope form, right? And we've worked with point-slope form a lot in the last unit. So essentially, if I do some changing of notation and make my y into f of x and my y sub 1 into f of a and my x sub 1 into a, and just kind of move it around, I end up getting this expression. And then this just formalizes it into what we call L of x, which is the linear approximation, or the tangent line approximation of f at x equals a. All right, and this whole idea is called linearization. So we're going to use this formula to approximate the value of a function at a certain value for x, all right, using the tangent line. So essentially, it's like instead of just plugging in the number into x, we're going to use the work that we did last unit on finding a tangent line to our curves. We can use that tangent line to approximate x values that are close to that x value where it actually intersects. And I'll show you graphically to kind of help this when we do one. All right, so let's try this first one. We're going to find the linear approximation of f of x equals the square root of x, so the basic parent square root function at x equals 9. All right, we're going to use that to approximate and estimate the square root of 9.1. So I'm going to write down this formula again, which is the linear approximation of x equals f of a plus f prime of a times x minus a. Okay, so what we need to do to find this is we first need to find f of a. All right, in this case, f of a is f of 9. So the square root of 9 is 3. So that's going to be my f of a. And I also need to find the derivative of this function. So let's find the derivative of this function, which is d dx of, watch how I write it, x to the 1/2 power. Using the power rule, that's 1/2 times x to the negative 1/2 power. Making it look a little nicer is 1/2 times the square root of x. So f prime of 3, not 3, sorry, f prime of 9 is going to be 1/2 times the square root of 9. The square root of 9 is 3. 3 times 2 is 6. So f prime of 9 is 1/6. Okay? So now, if I set up the linear approximation here, I have 3 plus 1/6 times whatever my x is, right? That's what we're going to plug in, minus a, which is 9. Okay? So it wants me to estimate 9.1. So I'm going to use the formula that I just did. I'll change colors to show you that I'm kind of like changing steps here. And I'm going to plug in 9.1. So 3 plus 1/6 times 9.1 minus 9. All right, so using decimals, I'll go there and then I'll show you what we did here graphically. So I'm going to do 3 plus 1/6 times 9.1 minus 9. Maybe not if decimals doesn't load. That would be disappointing. Okay, I'm going to pause and see if it can get it to load here. Okay, I got it to load. So we have 3 plus 1/6 times 9.1 minus 9. All right, so the approximation here is 3.017. So 3.017. All right, now just to kind of make sure you understand that we didn't just plug in or do the square root of 9.1 in our calculator, let me show you a couple of things. So we have let me graph the, let me first just do, a lot of students say, well, why can't you just do the square root of 9.1? You can, right? It's obviously very close. But the other thing I want to show you is when you graph the square root of x, right? And then when you graph that line, 3 plus 1/6. I know it kind of looks a little different, but this essentially is still our point slope form. I just moved over the y sub 1. I didn't distribute. And if you look, we are hitting it at 9 comma 3. So essentially now we're using the purple line. So let me duplicate it. We're using the purple line to estimate what happens when you plug in 9.1. So if I made this x value 9.1, you see I get the same thing that I got before, 3.017. All right, so that's essentially what we're doing here. That's what this linear approximation is. We're using the tangent line to approximate what the value would be on the curve. Now, this is great if you're using points that are close to the intersection point of your curve and your tangent line, right? So we have 9, let me get this away for a second. We have 9 comma 3 right here, and 9.1 is really close. But if I wanted to use this tangent line to approximate the function at x equals 1 or x equals 40, right? Those are not very close to x equals 9. So, obviously there are limitations on doing this, but the only reason I mentioned the just typing it in is because this is what actually calculators do, right? Calculators are approximating all the time to find out what the value is. Okay, so that's kind of the first basic problem here. Let's keep going. Let's do another one. The linear approximation of f of x equals the sine of x at x equals pi over 3, and we're going to use that to approximate the sine of 62 degrees. So I'm going to do my same formula, which is f of a plus f prime of a times x minus a. So I need to find f of a first. So f of pi over 3, which is the sine of pi over 3. If you still need to use the trig formula sheet, please use the formula sheet. This pi over 3 is the same as 60 degrees. I know the sine of 30 degrees is 1/2, and the sine of 60 degrees is the square root of 3 over 2. Now I'm going to find the derivative of my function, which is d dx of sine of x. We know the derivative of sine of x is the cosine of x. And then I need to plug that in, or plug in my x value, all right? I should say my a value when I evaluate here. So the cosine of pi over 3 is going to give me my slope. All right, so if the sine of pi over 3 was the square root of 3 over 2, the cosine of pi over 3 is 1/2. So that's my slope, or f prime of a. All right, so I'm ready to write it. Here's a linear approximation for any value you want to plug in. We have f of a, which is the square root of 3 over 2, plus f prime of a, which is 1/2, times x minus a. I'm going to use this to approximate 62 degrees, or the sine of 62 degrees. Now here's the thing, guys. What I just did was all radians, right? Pi over 3 is radians. So I'm going to do a little sidebar here and change 62 degrees to be radians. So multiply by pi over 180. All right, so this becomes 62 pi over 180. So that's what I'm plugging in. So the L of 62 pi over 180 equals the square root of 3 over 2 plus 1/2 times the square root of, let me change this real quick, I apologize. That a value was supposed to be pi over 3. Okay, here we go. Now we're back. So we have 1/2 times 62 pi over 180 minus pi over 3. At this point, please, if you're ready to go to Desmos, just go to Desmos and type this in. It will give you the answer. If you want to keep doing some more algebra, we'll do the algebra here. 62 pi over 180 minus pi over 3. I change pi over 3 to be 60 pi over 180, and 62 pi minus 60 pi would be 2 pi over 180. Then I have this 1/2 is going to multiply. The 2 over 2 is going to cross out to leave me with just pi over 180. So whatever this is the linear approximation of 62 degrees. All right, so let's go to Desmos. We can type in the square root of 3 over 2 plus pi over 180. All right, we got the square root 3 over 2 plus pi over 180. We get 0.883. Now again, if you wanted to see if this was, close to what we would actually get if you did the sine of 62 degrees, you could just type in the sine of 62 degrees and you would expect to get something around 0.883. I'm not going to type in 62 degrees. I'm going to type in, because this is in radians, right? If you go to the wrench, you'll notice I am in radians right now. So the sine of 62 pi over 180, which is 62 degrees, which is 0.883, right? A little different, right, as you get to the thousands and 10,000s, 100,000s place, but essentially a pretty good approximation. Okay, let's keep going. Now, we're going to do the same process here. It's going to be a little bit trickier because we do have the n, all right? But I'm going to do a little work here, again, using this formula, L of x, right, the linear approximation for our x value at a is going to be f of a plus f prime of a times x minus a, all right? So first thing I need to do is to find f of a, in this case, which is f of 0. So that's going to be 1 plus 0 to the nth power. Now, I know that there's an unknown there, right, that letter n, but 1 plus 0 is 1, and 1 to any power, right, even 1 to the 6th power, 1 to the negative 8th power. It doesn't matter because 1 to any power is the same as 1. So f of a, right, this is f of a, is equal to 1. All right, now let's find the derivative. The derivative of this, so ddx of 1 plus x to the nth power is going to be, using the power rule, n times 1 plus x to the n minus 1. And if you did the chain rule, right, the derivative of the inside, 1 plus x, well, the derivative of 1 is nothing, and the derivative of x is just 1. So actually, that is the derivative of this function. I need to evaluate that, right, to find f prime of a. I need to evaluate this at 0. So it's going to be n times 1 plus 0 to the n minus 1. All right. Now, just like before, I have n times 1 to the n minus 1 power. So again, it doesn't matter what n is. Even if you subtract 1, 1 to any power will be 1. So 1 times n, so n times 1 will just be n. So that is f prime of a. All right, so this linear approximation became f of a, which is 1, plus f prime of a, which is n, times x minus 0, right, because my a value is 0. And to clean this up a little bit, that's just 1 plus n times x. So this is the linear approximation of this function at x equals 0. Now I'm going to use that to estimate 1.01 to the third power. Okay, so you'll notice I'm going to be using my, let me write this down in different colors so you're good. My n is going to be 3, right? That's the power. And it looks like my x, right, is going to be 0.01, right? Because 1 plus whatever it is, so 1 plus 0.01 would give you 1.01. So here we go. So L, the linear approximation at 0.01 equals 1 plus 3 times 0.01, right? Well, 0.01 times 3 is 0.03, plus 1 is 1.03. Okay, hold on 1 second, let me check something. Okay, so essentially what I'm saying is that my estimate, so my estimate of 1.01 cubed is 1.03. So this is my estimate. I'll put the estimate squiggles. All right, and again, if you wanted to go to Desmos to see, it's actually pretty close. Okay, now let's talk about differentials. All right, now differentials, essentially what we're going to do in this part of the lesson is we're going to be using this understanding, which we talked about a ton in the last unit on derivatives. And all we're doing is we're kind of changing the way that looks. So we're actually changing it to look like this right here, where if you move the dx to the other side, we can actually call this a differential, all right? And we can use this to help find an application of finding those changes, right? The idea here is that this dy dx, they do represent changes in those values. Okay, so let's try this one here. Remember, I'm going to use the formula. dy, or the change in y, is equal to f prime of x times d of x, or the change in x. All right, so we're going to find dy for each of these and then evaluate it when x is 3 and the change in x is 0.1. Okay, so first thing I need to do is I'm going to find the derivative. So f prime of x equals d dx of x squared plus 2x, which is equal to 2x plus 2. All right, now I'm going to need to figure out what f prime of 3 is, right, because my x value is 3. So I'm going to do f prime of 3, which is 2 times 3 plus 2, which becomes 8. All right, now it tells me what dx is equal to. It's equal to 0.1. So my formula is dy equals f prime, let me do f prime of 3 times dx. So that's going to be equal to 8, which I already found, times 0.1. So 0.1 times 8 is 0.8. Now again, could you just plug that in? Absolutely, right? The idea is that this is our way of estimating what it would be if we were to plug it in. Okay, now let's do this one with some trig. All right, so I'm going to find the derivative of cosine, so d dx of cosine of x, which we know the derivative of cosine is negative sine of x, but I am going to plug it in. All right, so I need to do negative sine of my x, which in this case they chose 3. All right, so to find my answer, it's going to be f prime of 3 times dx, which is negative sine of 3 times 0.1. That is the answer. I'm going to clean it up just a little bit. I'm going to put the negative and the 0.1 in front times the sine of 3. So this is the answer for part B. All right, let's keep going. Let's try computing the change in y and dy at x equals 3 if dx is equal to 0.1. Okay, so this is a great problem that kind of continues what we just did for part A, and you'll kind of see that as we go through this. So it wants us to compute the change in y, which is the actual change in y. So I'm just going to label this as the actual change. And then this dy is the approximate change. Okay, and that's the one that we just did earlier. So I'm going to start with the actual change. So the actual change to go from x equals 3, so from x equals 3 to, now watch this, right? The change isn't to 0.1. That is the approximate change in x, or sorry, the approximate change in x, which would be 3 from x equals 3 to x equals 3.1. So I'm going to do f of 3.1 minus f of 3. Whatever this is would give me the actual change in my y values. So I'm going to do 3.1 squared plus 2 times 3.1 minus 3 squared plus 2 times 3. So whatever that is would give me the actual change. I'm going to go to Desmos to type it in. All right, so I'm going to do 3.1 squared plus 2 times 3.1, then minus, put these in parentheses, 2 minus 3 squared plus 2 times 3. There we go. Okay, didn't like that. What did I do? Did I put an equal sign in front? No. Too many. What did I do? There we go. Just take out the brackets. All right, so the answer is 0.81. That's the actual change when you change the x value from 3 to 3.1. So 0.81 is the actual change. Okay, so this would be delta y. Okay, now we're going to find the approximate change using that formula, dy equals f prime of your x times dx. All right, and we actually just did this earlier in the previous problem, part A, and we said that f prime of 3 was equal to 8 times my dx, which is 0.1, which is the same as 0.8. So you can see that the approximate, right, this is the approximate change in your y to the actual change of y is pretty close. All right, so that's what essentially what we're doing when we use the differentials. Okay, now we're going to use that same idea to help us figure out some issues with computing the air in the volume of a cube. So this is we're going to take a little bit of detour from here and try to figure out the relative air and the actual air and things like that. So that's what we're doing in this example right here. Okay, so I'm going to do part A first, and we want to use differentials to estimate the air in the computed volume of this cube. So the idea here is we have a side length of a cube is measured to be 5 centimeters with an accuracy of 0.1 centimeters. That means our accuracy could cause it to be for either plus 0.1 centimeters or minus 0.1 centimeters. Okay, so the idea here is that the volume of this cube is the same as, let me actually start with first, is that the change in your x, all right, the change in your side length of your cube could be off by as much as 0.1 centimeters in a positive direction or 0.1 centimeters in a negative direction. So the idea here is that we're going to be using dx is either a positive 0.1 or a negative 0.1. Now the volume for a cube is psi cubed. In this case, we're going to use x cubed. So to find the derivative of this, it's going to be 3x squared. All right, so I can use that formula like we used before for the differential. All right, so that dv is equal to, by the way, great letters, is equal to the f prime, one second. Sorry, dv is equal to the derivative, 3x squared, times our change in the x, okay, like we've done in the past. So that means I'm going to plug in, right? But the idea is my change in my volume could be a little bit above or a little bit below. So watch the work that I do here. So it's going to be 3 times 5 squared times positive 0.1. And on this side is going to be 3 times 5 squared times negative 0.1. So the idea is that that one's going to be a negative. All right, and so if you do the math here, if you do the 3 squared, 5 squared is 25 times 3 is 75 divided by, or multiplied by negative 0.1, you get negative 7.5 compared to positive 7.5. So we're saying that if we use differentials, we're estimating that the air in the computed volume of the cube, so the approximate air, would be anywhere between negative 7.5 cubic units off all the way up to positive 7.5 cubic units off. So somewhere in between. Now, part B is where we're going to actually compute and compare it to the estimated air with the actual air. All right, so we're going to actually find the air if the side length were to have been 4.9, so 0.1 centimeters below, or 5.1 centimeters, which would be 0.1 centimeters above. So we're going to first find the volume if it had 4.9 centimeters as my side length. So that'd be 4.9 centimeters cubed. I'm also going to find it if it had been 5.1 centimeters cubed. All right. So using Desmos or just using a regular calculator, you would find that the 4.9 volume is 117.649 cubic centimeters. And for 5.1 as the side length, that would give you 132.2 0.651 cubic centimeters. Now, what most students want to do when they see this is they want to subtract that. But remember, these are the kind of the farthest reaching possible values for the volume if you had the worst accuracy in terms of measuring the side length. But if right down the middle, right, if it was perfectly 5, right, it would be 5 cubed, which is 125 cubic centimeters. So essentially, to find the actual error that could occur here, we need to subtract from 125. So we're going to do 117.649 minus 125. Okay, and this would be the change in the volume. And compare that to 132.651 minus 125. So whatever these are would give us the actual potential error that we're expecting, and we're going to compare it to what we estimated. All right, so 117.649 minus 125 gives you negative 7.351 cubic centimeters. And going the other way would give you 7.651 cubic centimeters. So I'm going to try to show you the comparison here. Right? We said we approximated the values to be somewhere between the volume would change by negative 7.5 to 7.5 cubic units. Right? When you look here at the actual, right, potential error, it's really close. Maybe not as far left, and then a little farther to the right, but pretty close in terms of what we calculated as the approximate versus the actual. All right, now one more slide before we finish this lesson about finding relative and percentage error. All right, we're going to talk about the using the Earth as this example. Okay, so on this one, we're going to be looking at finding the estimating the relative and percentage error of using this radius to calculate the volume of the Earth, assuming that the planet is a perfect sphere. So that's going to require us to know the volume for a sphere, which is 4/3 pi r cubed. All right. Now, the first thing I noticed is it tells me that the astronaut measures the radius as 4,000 miles with an error of plus or minus 80 miles. So my measurement error for the radius is plus or minus 80 miles. So my dr is going to be plus or minus 80. All right, so using kind of the same process that we did on the previous problem with the volume of a cube, we're going to find what would be the propagated error, which is just a name that means the error in calculating the volume if you make an error in measuring the radius. So making an error earlier on is going to cause the y value at the end to be incorrect, and that is called a propagated error. So I'm going to find, let's write down the change in the volume. So dV, the measurement error in the volume, would be the derivative of volume, which is power rule 3 times 4/3, which is 4 pi r squared times dr. So I can use this to find my error in measuring the volume. Okay, so if it's the astronaut really undersold the radius by 80 miles, all right, then it would be 4 pi times 4,000 squared times negative 80. And then if it was the other direction, it'd be 4 pi 4,000 squared times positive 80. All right, and this would give us, right, the measurement error. But to find the relative error, we would have to take these errors and divide them by what we expect the actual volume to be. All right, and this can be more helpful usually, because if you just tell me how much error happened, okay, great. But if you tell me that it relative to what I expected it to be, I could actually quantify whether that was a big deal or not a big deal. So I'm going to divide both sides here by the volume if I were to assume that the radius is actually 4,000 miles. So I'm going to multiply times 4/3 pi, and then my radius is 4,000 cubed. Same thing on this side. All right, now I'm going to go to Desmos and type this in, at least one of them, so you can see what we get for the relative error. And then to find the percentage error, It's just you take that and turn it into a percentage. So just move the decimal over 2 places. All right, so let's type in the numerator, which was 4 times pi times 4,000. I'm going to do the positive one, but it doesn't matter. Squared times 80 all over 4/3 pi, and then the radius cubed. Right, you get 0.06. So that's the positive version. So I'm going to write 0.06 there. And the negative version would be negative 0.06. So we're expecting the measurement error in terms of the volume, right, to be somewhere between negative 0.06 and positive 0.06 cubic miles. All right, but again, this is all relative, right? I don't really know. I can't quantify in my brain what 0.06 cubic miles is. So if you make this a percentage, right? Make this a percentage. We're saying that the percentage error possible is 6%. All right, and that's something that the people at NASA will have to decide. Do they want to live with 6%, or do they want to have the astronaut go back and take different pictures? All right, so hopefully this will give you an idea of what we're talking about with linearization and then getting into some differentials.